Welcome back to the channel. Imagine a car that never rolls in corners, never dives when braking, and glides over bumpy roads. No expensive active suspension, just 4-in wheel motors. Today we are breaking down a brilliant paper by a Toyota chief engineer. We'll see how a few lines of math can completely hack a car's physical limits. This is part 1 of our 2-part series. We'll start with the basic physicals and review the paper's biggest breakthrough: how to break the rules and use simple driving and braking forces to achieve full 3D degree of freedom control. Let's head to the whiteboard and enjoy this hardcore derivation together. Now, let's use in-wheel motors. We'll build equations to control the vehicle's degrees of freedom. First up is the longitudinal motion. Here, Fx represents the longitudinal force. The equation goes to Fx equals Fx Fl. Here, Fx Fl means the front left longitudinal force. This is left and this is right, plus Fx Fr, front right longitudinal force, plus Fx rear left, and plus Fx rear right. Okay, this is the first equation of longitudinal force. Next is heave. This is the paper's absolute core. How can a longitudinal force control vertical motion? Let's look at the second figure. The front and rear wheels pivot around their suspension rotational centers. This is a direct result of the suspension geometry. Theta F and theta R are the angles. They show where the rotation axis meets the ground. So, when we apply a longitudinal force, the rotation axis does something special. It automatically creates a vertical force component. Specifically, look at the front wheels. Apply a forward driving force. The suspension axis turns this into a downward force. This pulls the whole vehicle body down. Now, look at the rear wheels. Want to pull the car body down here? You need a backward braking force. This drags the suspension and pulls the body down. Notice something important here. To get a downward force on both ends, the longitudinal forces must go in opposite directions. Again, this is all due to the suspension geometry. Next, let's see how to generate an upward force. Let me change the pen color. To push the car up, the front wheels need a backward force. That means braking. The rear wheels do the exact opposite. They need a forward driving force. Once you grasp this trick, everything else clicks. Controlling heave and other degree of freedom becomes incredibly simple. Now, let's look at the heave control equation. The formula for Fz is here. To push the vehicle up, the front axle needs a backward longitudinal force. This is minus Fx-Fl plus Fx-Fr. Multiply this by tan theta f. This gives the lifting force at the front axle. To lift the rear, the longitudinal force is opposite to the front. So, it is plus Fxrl plus Fxrr. Then, multiply by tan theta r. Next, let's look at the roll control equation. The vehicle turns right. This creates a roll motion. It requires a downward force on the left side and an upward force on the right side. So, we can express this control equation as mx equals left side goes down. This needs a forward longitudinal force. That's positive Fxfl. Right side goes up. This needs a backward longitudinal force. That's a negative Fxfr. Multiply by tan theta f to get the vertical force. Then multiply by Tf over 2. Here, Tf is the front tread. The situation for the rear wheels is the opposite. Left side goes down. The longitudinal Fxrl is negative. Right side goes up. We use plus Fxrr multiply by tan theta r, then multiply by Tr over 2. Tr is the real thread. Now, let's check the pitch control equation. Let's assume a forward dive. My equals the front axle needs a downward force, so the front longitudinal force is positive. Multiply by tan theta f. Then multiply by Lf. Here, Lf is the distance from the front axle to the CG. The rear axle needs an upward force. The longitudinal force is also positive. That is Fxfl plus Fxrl times tangent theta r times Lr. Lr is the distance from the rear axle to the CG. I want to write that down here. Finally, we have the yaw control equation. Erase this part first. Let's look from above. Assume a counterclockwise yaw. The right side of the vertical needs a forward longitudinal force. The left side needs a backward longitudinal force. So this equation is minus Fxfl plus Fxfr times Tf over 2 plus minus Fxrl plus Fxrr times Tr over 2. Alright, we have now completed the equations. We can use in-wheel motors to control 5 degrees of freedom of the vehicle. Now, let's plug these control strategies in the motion equations. There is a key point here. Height and pitch cannot appear in the same set of motion equations. Why is that? When we build control strategy for these 5 degrees of freedom, we follow a fundamental rule. The applied control forces must never interfere with the driver's normal intentions. If we apply a forward control force, Ff, we must also apply a backward force, Fr. These two forces must be equal in size, but opposite in direction. Let's assume this value equals delta F. Now, let's substitute delta F into the height and pitch control equations. Fz equals, here Ff is the sum of front, left, and right longitudinal forces. Fr is the sum of the rear longitudinal forces. Fz equals minus delta F times tangent theta F plus minus delta F times tangent theta R. This simplifies to minus delta F times tangent theta F plus tangent theta R. Now, let's look at the pitch. My equals minus delta F times tangent theta F times Lf plus minus delta F times theta R times Lr equals delta F times tangent theta F times Lf minus tangent theta R times Lr. Let's compare the equations for height and pitch. The terms inside the brackets are just the basic vehicle parameters. Both height and pitch contain the variable delta F. This means something very important. If we want to apply an upward force to control the height motion, we will inevitably create a pitch dive motion. In engineering, this is called motion coupling. Therefore, height and pitch motions cannot be controlled at the same time. Alright, that wraps up this episode. We covered the first 3 chapters of this paper. We mainly focus on building the control equations. There are quite a few formulas involved here. Please feel free to rewatch this section a few times. If you have any questions, just leave a comment below the video. These equations are the foundation for autonomous vehicle attitude control. Once you master them, you will see that all other control logics are just an evaluation of these basics. In the next episode, we will explain how to plug this control strategy into the kinematic equations. We will also explore the author's innovative motion decoupling strategy. Thank you everyone, and see you next time.